Hello world, and welcome to this tutorial on writing a Hello World program in x86 assembly language by comparing it to a C Hello World program. By the end of the video, I hope you'll have gained knowledge on the general structure of an 86 assembly and how the code is executed. Now, the concepts might be hard for beginners, but rewatching the videos and finding other resources might help cement the general idea. I'll explain it to the best of my ability, and I'll link some of these resources I found useful while I was studying assembly. If you look at our code, the first thing you'll notice is that the program has been divided in two sections, the data section and the text section. This is a requirement for assembly code, and it has a very good reason, but C doesn't have such a rule, therefore it's a new concept to us. In assembly, most of the code you write should be placed under a section, which is basically a category. So these sections tells the assembler where you can find what type of data. For example, as you can see in this table, the initialized variables, which are variables that have both been declared and given a value, are stored in their own sections, while the uninitialized ones are stored in a different one. Constant variables are also given their own section, and the main program or code which should be executed, which contains the main instructions, should be stored in its own section. There are many other sections in assembly, but in our case, we want to store the value that we want to be printed in a variable, and that is going to be the message variable. And we have to do it in the data section because it has been declared and it has a value, which means it has been initialized. So while comparing the C variable to the assembly variable, we can see that they have some things in common. The first one is that they both have a variable name, which is a name that we can choose to our liking so that we can use it later in the program to call this value. Which is almost similar to this is called a define byte, and its job is to define a variable by assigning a byte to each character of the value. So in our case, the value being stored is hello world, and it has 13 characters. Therefore, the define byte keyword allocates 13 bytes to the variable message. Next, we have the value itself, which is enclosed in quotation marks, and it's quite self-explanatory. Finally, it ends with a 0, which is called a null terminator. Now, the null terminator is a special character which will be appended at the end of the string in the memory, and it's used to show that the string has ended. This is very important as it is used to prevent an error called the buffer overflow. In C, we don't need to add it to the string itself, as the compiler does it automatically. That is how we initialize variables, or string variables at least. The next section we have is the text section, and as you can remember from this table, it's where the instructions or the code itself is put. Now these are the instructions that are going to be run by the assembler. We'll begin by defining the program's entry point, and in our case we'll call it underscore start, which is almost similar to C's main, but it has some few differences. The first difference is that in C, main is a function, and in assembly, this start is not a function but rather a label, as functions are a different concept. The second difference is that in C, main is automatically known as the program's starting point, but here in assembly, we have to tell the assembler that our starting point is start. So we'll have to use this global keyword which tells that start is our entry point. After that, we'll begin implementing the print method. As you can see, in assembly it uses 5 steps to implement what C does in one step, and it's for a good reason. To understand what the program does, we'll have to begin at the last part here. It's also called the system call or the system interrupt, and it serves a very special purpose. It's the core of all the functions we see in C. So, what's a system call? So we have to know that when we are doing things like displaying a number to the console, or displaying a message to the console, or killing a process, or reading a file, what we are generally trying to do is interacting with other programs in the operating system. In a language like C, these actions have been given names and they have been simplified. For example, to print data to the console, we just use printf and pass the data we want to print, or scanf to get data from the console. However, as you might know, assembly is very low level and we have to do almost everything ourselves. Therefore, to alert the OS that we want to use another operation, we have to use what is called a system call. However, since assembly does not have functions, we cannot pass arguments to function just like as we do in C. We therefore have to utilize something called registers. Now, don't worry, registers are simply memory locations. You can think of them as named memory locations that can be accessed very fast and are therefore set aside for the processors to use. These are the registers in C, and you can find them in a table which I've attached at the description. So when a system call is invoked, it checks the data in the registers and tries to do whatever it's been told. It first starts by checking the register EAX, and it is in this register that the code of the operation you want to be performed is stored. As you can see in this table, there are many processes that can be invoked by the system call, and these are their codes that you have to put in the register EAX so that the processor will know which operation you want to invoke. I've also added a link to more detailed tables for the above processes in the description. So as in our case, we want to tell the system that we want to print to the console. So in the register EAX, we'll move the code to indicate that we want to write, which is code 4 according to this table. Now that we have done that, we have to know one more thing. The write operation, system write, uses 3 values in order to be successfully complete. This is what it looks like when treated in C notation. So as you can see, the first value it receives is called the file descriptor, and it simply tells where we want to perform our write operation. So for example, when we want to write to the OS, so as you might have guessed, there are codes for these two, and passing 0 as the file descriptor tells the operating system that we want to write to the standard input. Passing 1 tells the OS that we want to write to the standard output, and passing 2 tells that we want to print an error. And using any number of 3 and above tells the OS that we want to write the message to a file which has been opened somewhere in our program. And as you might remember, assembly is not like C, and we don't have clearly defined system calls like system write. So in our case, we have to pass the data manually to the next register available, which is register EBX. The second argument we should pass to the system write method is the buffer, which is simply the message we want to print. And in our case, it's a variable message. And just as we did to the first variable, this variable will be passed to the next available register, which is register ECX. And finally, for some reason, we have to tell the system the length of our message. And as you can see from here, our message is 13 characters long. So we'll pass 13 to the next available register, which is register ECX. To recap what we've just done, we want to tell the system that we want to write, and we'll therefore move the code to write, which is for register EAX. Next, we'll pass the first argument, which tells the OS where we want to write our message. And since we want to write to the console, we'll pass 1 to register EBX. After that, we have to pass the message that we want to write to register ECX. Finally, the length of the message to register EDX. And now, since we have clearly defined what we want to do, we'll now invoke the system call itself. And that is how you write a print operation in x86 assembly. Now that we have finished writing, we have to exit and return 0. As you may remember, there is no function for us to do this, so we have to define everything ourselves. So just for comparison, let me add the other system call we performed so that you might see the trend we are setting. Just like the previous system call, we'll have to move the value of the code that we want to use. So in our case, we want to exit, and exit is system code 1. So we'll have to pass 1 to register EAX. As you can see, exit only takes one value, which is the exit status, and 0 is used to indicate that the program has executed successfully. We therefore pass 0 to the next available register, which is register EBX, and we finally complete the operation by performing the actual system call. That is a simple hello world program in assembly. Please remember to like, subscribe, and comment in your thoughts and feature requests. Thank you.